because that's the most important part. Otherwise, it didn't happen. Yes, I had someone comment on the YouTube videos from Tuesday when I asked folks, "Can everyone see me?" They wrote, "We cannot see you." On the comment. Yes, I know. There will not be a video of my face talking on the internet. That is not going to happen.
Understandable.
That's a good line.
Yeah. No, I actually hate having my picture taken. I hate it so much that, do you know what it says in my senior year yearbook next to senior pictures? It says, "Not pictured," with my name, because I did not take senior pictures.
Oh, oh my gosh.
Having my picture taken that much. There's like 4 pictures that exist of me on Earth. So I'm not putting my video online. You get to see the lovely materials, and you get to hear my lovely voice, and that just has to be enough for my dedicated YouTube group. I'm not selling this, so I figure, it's just a recording of class for folks who are not able to make it or who want to hear the material again. That's the objective. So, anywho, so updates. Let's see. You have your next homework available that you can start, and I wanted to point out that I added a resource that is posted on the course webpage. I forgot to bring that up, so let me do that real quick and show you where that is. There we go. So on the due date for your next homework, which is, let's see, the 28th, so like 10 days from now, I made a new handout called Steps for Doing Homework. So the process for doing homework, I know there's a lot of files you have to have open, and there's an order, and there's things you have to change and don't change, and I fielded a number of questions on that, so I thought I would just write out the steps. So every time you do a homework, these are the steps that you follow. And one thing I did want to point out is that it's very important to read the instructions at the start of the homework, because that's where I describe what the variables mean, what your objective is, and what exactly you're supposed to do. And within my examples, so all of these handouts that I'm going to be creating throughout the semester start with data import and data manipulation code. That part you do not use in your homework, because I put starter syntax online that imports your homework data if you change the path and your number, and it tells you what all those variables are in the context of the homework. So when you go through these sorts of example documents, the only things that you need to be borrowing with respect to doing homework are the modeling pieces. So it's proc GLM commands in SAS, regress commands in Stata, and LM commands in R. Those are the things that you want to copy the code and paste it into your homework syntax and modify. And if it doesn't work, you should check 2 things. Number 1, did you change the name of the data set? So it should say homework 2 instead of example 2. And number 2, did you change the name of the outcome variable? So the story behind homework 2, fitting since we were just chatting at the beginning of class about Montessori school, which is my son has been since he's 3. He is 6 right now. The story behind your homework is a preschool classroom that was observed with a group of 3-year-olds and 4-year-olds, and the number of fits thrown was recorded by an independent observer, as well as the number of pleases heard. And so your regression models are going to be looking at the relationship between fits thrown as an outcome and pleases heard as a predictor, as well as the effect of age on number of fits thrown. So those are the variables as part of the story. As a parent, I can attest 100% accuracy in all of these simulated relationships. So you would know exactly what the variables are called and exactly what the model should look like at each step per the instructions. And if any of the instructions are unclear, please let me know, because I can clarify the wording and change the text very easily to make it work better. So just a few additional resources there for folks to figure out homework. And if you'd like to come to office hours, pre-pandemic, at my other jobs, I used to hold office hours in a computer lab like this, and students would just come and hang out, and they'd use the time to work on their homework. And that way I would just float around the room and help people, and they could get back to, they could keep working and not get stuck. And that's what I intend for office hours to be. So you can log in, sit in the background, pop into the chat if you have a question and get my attention, and then, go back to the background and work if you want to. Or you can just pop in randomly, ask your question, and leave. So it's in Zoom, so hopefully it's not like you have to drive somewhere and wait in line or any of that kind of stuff, but please don't hesitate to reach out. And I've been talking to my TAs, and they're lonely. The 3 TAs for this class have let me know that they're not getting visited very much. So that's another resource for you if my hours are not convenient. Those folks are happy to help you, and they're either getting course credit or money for doing so. So they're getting something out of it too, in addition to teaching experience. So just a few things about that. Any questions about logistics, schedule?
I was wondering about the formative assessments.
Mm-hmm.
I know that we get 100% if we do it.
Yep.
But I was wondering, what the feedback on that looks like. If I totally botched it up, is it just when I listen in on Tuesday, I'll know if I botched it, or is there specific feedback given?
What I do, so it's due on Monday nights, so that I can log in Tuesday morning and I read through everyone's stuff, and I usually leave a comment, good job, or I answer, or see my comment on your response to this. Mm-hmm. So I leave brief comments into your answers. I tend not to provide detailed answers because we're going to go over it in class.
Okay.
But you should see my comments, and if I haven't gotten to it yet, it may be because you turned it in after Monday night, or because somehow I just accidentally missed it. Mm-hmm. I tend to check back every few days to make sure that I've caught up on that. So if I missed it, let me know. But yes, it's the formative assessments. You get 2 points for doing it. If you put forth an honest effort, and an acceptable answer would be something like, yeah, I have no idea what you're talking about. That's a fair answer. Because if enough people say that, then I know that something went awry on my end, right? So there's the two-way street here in terms of communication that helps, because not everybody is brave enough to talk during class, or type, as it were. Okay, so new stuff on tap for next week then. I posted Lecture 3, Example 3, and then the corresponding files that go with it. So we're taking what we're doing this week and upping the level of complexity somewhat so that we can look at different kinds of relationships. So where we've been so far is looking at how to predict quantitative outcomes from one type of predictor. So far we've covered a single quantitative predictor and examined a linear relationship of that predictor in creating expected outcomes. And then today we want to do the same thing for a binary predictor because it works the same way. Next week we'll talk about what happens if you have, say, more than 2 groups for a predictor, or you want to look at a relationship that's nonlinear in form. So that's what's happening next. So exciting new stuff. And we're already like a third of the way through the semester. Can you believe that? It's week 5. So it's going quickly, maybe, or maybe for some of you it's going slowly. But I felt like maybe we could use a little bit of a pep talk, point that out that you have made progress. And the thing about this material is that I know it can be overwhelming. I know that there are a lot of moving parts that are all at the same time, and a lot of concepts and a lot of words and a lot of symbols and equations, and it can be easy to feel like I'm never going to get this. But that type of feeling is unavoidable when you're trying to do something new for the first time. Like, I remember what it was like when I tried to learn how to drive a car. And at first, the idea of using like 2 different pedals and steering and doing the turn signal and checking in front of me and behind me, and then we're trying to remember, like, okay, do I yield here or do I not yield? Like, it was completely overwhelming. And eventually you get to the point where it's less overwhelming, and then you kind of take it for granted. Does anyone here know how to play piano? Few people? Yeah, so I tried to learn how to play piano as an adult, and it was the same thing. It was like, so you're telling me that my right hand has to do something different from my left hand on different counts and different notes at a different tempo, and you want me to use my feet too? Are you kidding me? And the first time that I ever got both hands working at the same time, it was like, oh my God, I finally did it. I was terrible. I remained terrible. It did not sound good, but I successfully executed the notes, and then eventually it got a little bit easier. Or if you've trained for a marathon, like if you do like the couch to 5K, the first time you try to run, I went running yesterday for the first time in like 3 months. I am paying for it today. My legs hurt. And I could feel bad about that because I could think, well, I used to be able to run 6 miles and now I can barely do 2. What's wrong with me? Or I could feel good about the fact that I just did 2 miles for the first time in 3 months, and that's progress. So I know that it can be easy to get discouraged. I know it can be easy to get down on yourself because you feel like you're the only one that's struggling. You're not. It does get easier. And everything that we do is not unlike adding mileage to your long run. So when you're training for a long event, like you might run 3 miles on one Sunday, and then the next Sunday you try 4. And then 2 Sundays after that you try 5. And then 2 Sundays after that you try 6. And the part that's easy to forget is how much further you're going before the new part hits. Like that long run, you know, the last 10 minutes or the last 12 minutes are just going to suck. Like that's just what's going to happen. But then you forget, oh wait, I just made it 5 miles and before the suck started. So everything that we add this semester, it's like we're going to add a little bit each time, but getting to that little bit more is going to require going back over all the things before it. So there's going to be a built-in repetition and rehearsal that will make things seem like they're more familiar because they will be by then. So I'm saying we're a third of the way there. Hang in with me. It's going to be okay. All right? The Zoomers are like, yeah, Lisa, you're high. I don't know about that. Just have faith. I said not to trust me, but have faith. It'll be okay. So big picture, what have we been learning? Tell me anything you remember. Linear models? Yeah, that is what we've been learning.
And then centering in the SAS, theta, and R.
And what the last part?
Centering.
Centering?
Yeah.
Centering, yeah. We're rescaling predictors so that 0 means something. And we do that so that the intercept of our model, which is the reference point for where the linear model starts from, so that that thing makes sense. Yeah. In life, why would you fit a linear model? Why am I making you learn this?
If your x equals 0, if your x equals 0, what does that mean in your y, I think?
That's what the fixed intercept means.
Oh, okay.
That is true. But my question is more general. Like, why are we doing this?
Like we would like to predict some fact.
We'd like to predict something, yeah. And we got a question to help predict something from data, yeah. The big, like 10,000-foot view is to answer research questions. People collect quantitative data because they want to explore relationships in the data. They want to know what relates to what, and if 2 things are still related after you factor in a 3rd thing or a 4th thing. All of those types of questions are answered with linear models. Now, the details of what goes into the model and exactly how it works depends on what kind of data you have, but the linear model is the machinery that runs all of this. So I know it can be overwhelming to get lost in the details, but the big picture is that you are here to become better researchers, to have more tools in your toolkit to work with quantitative data. That's the big picture. And research questions are often phrased as is this related to that? Or can I predict this outcome with this predictor? They're phrased as yes/no questions. And so the series of decisions that we're setting up with respect to, well, is it a significant slope or a not significant slope, is the answer to that question. And there are 2 things that make your slope, describing a relationship between 2 variables, more likely to be significant. One of them is sample size. All things equal, more people, more likely to have a significant relationship. The standard for where unexpected starts in terms of deviation from expected fluctuation, that standard is easier to meet the more people you have. The other one is something that we haven't talked about yet, which is on tap for today, which is effect size. And that terminology is exactly what it sounds like. So how big of an effect do you actually have? And how can we express that in a way that is general enough that anybody could look at that number and go, yeah, I know what that means. And you don't have to know exactly how X is measured and exactly how Y is measured to answer the question. So all things being equal, stronger effects are more likely to be significant. So we have to figure out how to describe what we found in a way that's general and to evaluate in a more absolute sense just how strong of a relationship we have. So in what we've done so far, for instance, we get to where we were, centered education. We were predicting outcomes from the model with these linear combinations before. We end up with a slope of 1.82. Now I can look at this p-value right here. And the fact that p is less than 0.0001 tells me what? Significant, thumbs up, or non-significant, thumbs down? Oh, we got a mix of thumbs. Significant, thumbs up, or non-significant, thumbs down? This one's significant. P less than 0.05 is the alpha cutoff here for where unexpected starts. So if the slope were 0 in the population, we would see a slope this strong less than 0.01% of the time. But how big of an effect is it? Well, for every year of education, you're predicted to make $1,800 more. Okay, but is that a lot? Ooh, well, I don't know. How big could it be? Like if this were a perfect, lockstep, 100% certain relationship, how big would the slope be? Well, I don't know. Because I have to know the units, right? I have to know that this is years of education. I have to know what we're predicting, which is thousands of dollars. I'd have to know what the variability of each of those things is. I'd have to know what the mean of each of those things is. So trying to find a way to quantify just how big that number really is requires a lot of additional information. There are lots of different ways to quantify effect size. The first one that I want to show you is one that you probably already know. I can turn that slope into a Pearson correlation. Are those words that mean anything?
I think I've heard them before.
I've heard them before, right? An R, a correlation. Here's a slide on that. Slide 48. I wasn't sure if you'd remember Pearson's correlation, so I'm asking the question. Do you remember a correlation? Because this is one of the things that they probably went over in intro stat, however long ago that was for you. It is an index of what's known as a bivariate association. Bivariate means two variables at a time, just like we have in our linear model. So far we got one x, we got one y. So Pearson's correlation is the slope between two variables that have been standardized to the same metric. The metric they've been standardized to is a mean of 0 and a standard deviation of 1, otherwise known as a z-score. So I'm on slide 48 of lecture 2 here, and I've got pictures. So R stands for correlation. You'd think it'd be C, but it's not. It's R. I don't know why. It just is, but the entire world agrees that it's R. This is one where there's no ambiguity here. R goes from positive 1 down to 0 down to negative 1. And a perfect positive relationship is an R of 1. That means as you go up in one standard deviation in X, you are guaranteed to go up one standard deviation in Y. So the data would have to look like that, like a perfect correspondence. An R somewhere between 1 and 0 would look like these patterns in here, where there's a positive correlation. A one standard deviation increase in X is still corresponding to some kind of increase in Y, but it's not perfect. If two variables are completely unrelated to each other, that's an R of 0. So that would be a flat slope. A standard deviation increase in x, it corresponds to a 0 change in y. They have nothing to do with each other. And then as we head towards the negative side, it's the exact same concept, but the direction is backwards. So a perfect negative correlation of -1 would be if for a 1 standard deviation change in x going up, you get a 1 standard deviation change in y going down, a negative slope. So what to pay attention to in R with respect to the size is the absolute value. So an R of 0.8 is just as strong as an R of -0.8. So this is a metric that if you tell someone, oh, it's a correlation of 1, they know that that's as good as it can possibly be. You don't need to know whether it's in dollars or years or weeks or pounds or inches or what. Pearson correlation is one kind of correlation. There's like 87 others. But ones that you may have heard of, if you have 2 binary predictors, the correlation between them is sometimes called a phi correlation. That is the same thing as Pearson. It's just a simplification of the formula to compute them. If you have a correlation between a binary variable and a quantitative variable, that's sometimes called a point biserial correlation. For those of you who are in measurement class, you may have learned about that as item discrimination. If you have binary items correlated with the test score, that's point biserial. That's this too. That's just a computational shortcut, but it's still a Pearson correlation. So the ingredients to Pearson's correlation are means, variances, and something called covariance, which is an association in unstandardized units. I kind of skipped over that because we don't use it a lot for anything else, but it's in your textbook. So what if I told you that everything that we've done for the past month is just this? Would that blow your minds?
Feels a lot more complicated.
It feels a lot more complicated. I know. But it turns out that if I take my linear model and I convert my x to a z-score, so it would be x minus the mean over the standard deviation of x, and I do the same thing for y, and I fit a linear model, the slope I get back is Pearson's correlation. So then the logical question beyond that is, okay, Lisa, why did you make us do all that other stuff then? Why did you make it so much more complicated? That is a fair question. The reason is that Pearson's correlation is only capable of indexing certain kinds of relationships. So we have a question in the chat. So linear models are the same as Pearson's, and then a face that looks like a surprised face, I think. Surprise emoji. It is in this one, in lecture 2 it is. Because what we have so far is a quantitative predictor and a quantitative outcome and a single slope relating the two of them. And that slope, if you look at the pictures here, what kind of slope is it?
Negative.
This one's negative, this one's positive, but in terms of the form of the relationship. Is it straight or bendy?
It's like straight linear? Is that
Straight linear,
Yeah.
yes. It's a line, linear, as they say. Yes, it's a linear relationship. Well, what if I wanted to examine whether 2 variables had a non-linear relationship, such as the relationship between education and income? Do you think having more education has the same bang for your buck between 7th and 8th grade as it does between, say, 12th and 13th grade? Probably not. Can Pearson's correlation do nonlinear relationships? Nope. What if I had a nominal predictor? I want to examine differences in annual income between teachers, engineers, rock stars, and basketball players. Could I ask that question? Is that question possible to be answered in life? Sure I could if I could collect the data. I'm not sure how compliant basketball stars are at filling out surveys, but in theory they could have a personal assistant do that for them and report the billions of dollars they make for being a basketball star. But can I do that with Pearson's correlation? I cannot. Because I would have to come up with a way to indicate differences between each of my groups, and the grouping variable is not a number. It's categories. This has to be a number for this pattern to make sense. Another thing I can't do with Pearson, what people use linear models for, is asking if something still matters after controlling for something else. Is there still a relationship between academic achievement and socioeconomic status after you control for parenting whatever? That kind of question. Are these two things related after factoring in a third thing? Pearson correlation can't do that either because it's a bivariate association, two things at a time. So I swear I have not wasted your time, because even though in this one specific case of one quantitative predictor of one quantitative outcome and a linear slope, it's the same as Pearson's correlation, the general linear modeling machinery is much more general. And it allows you to answer all kinds of other questions that Pearson's correlation cannot. But we can borrow Pearson's correlation to provide us with an effect size for our model slope. And there is a way to do that. I'm backing up to slide 47 here. We're going to ask it to give us something that's called a standardized slope. This is a very common way of indexing effect size in general linear models, but it is not the only way. But in this case, it's the one I want to show you first. So I can ask the software to do this for me, but if you want to know how to do it yourself, I can compute a standardized slope by starting with the unstandardized slope and adjusting it for the standard deviation of my X predictor and the standard deviation of my Y outcome. In a standardized solution, the fixed intercept will always be 0. Free homework question. That's at least two or three questions on your next homework. What's the standardized intercept? It's 0. This is your bonus for coming to class. That one is 0. So if I take this information here and I feed in the standard deviation of X and Y and the unstandardized slope of 1.82, I come up with a standardized slope of 0.38. So that gives me a little more context as to how related education is with income in a linear relationship. It's positive. It's not a lot, though. It's sort of medium-ish. What's the highest that this number could be in a standardized slope? 1. And if these things had absolutely nothing to do with each other, what would this number be? 0. So 0.38 is my correlation. So this matters for two different reasons. One is because given that significance is a function of sample size, just saying whether the slope is significant or not is not enough information. We also want to provide an effect size measure for that slope in a metric that people recognize and know what to do with. That is scale-free, as they say. So what this means is that for every standard deviation increase in X, Y is predicted to go up by 0.38 standard units. That's what that means. That may not help. But if you look at this number and go, well, it's somewhere between 0 and 1, but it's closer to 0, it's a positive relationship, so I know that as education goes up, income goes up, but it's not like a lockstep, guaranteed, perfect relationship. So that's one reason we need this, is just to describe the size of the effect that has nothing to do with sample size. The other then is to figure out what the sample size is that we would need to have a good shot at finding the slope to be significant. So what am I talking about? Trying to figure out what kind of sample size I might need to have a good shot at finding something. What does that sound like? Does that sound familiar? If you do a grant proposal, you need to figure this out. If you do a dissertation proposal, you probably need to figure this out. We're talking about a power analysis. Sample size planning. That's what effect sizes are often used for. So we'll talk about that hopefully today as well. So even though I have the formula here, I don't want you getting out your calculators. There's only 1 or 2 numbers throughout this entire class that I'll need you to compute yourself, and I'll let you know when that happens. Instead, we are going to ask for the slope to be standardized ourselves. So I am on page, let's see here, 8 of example 2, showing you how to get standardized slopes out of general linear models. In this case, because there's only one predictor and because it has a linear relationship, it's the same as Pearson's correlation. In SAS, it requires a different routine, proc reg instead of GLM. That stands for regression. Otherwise, the structure of it is the same. In SAS, you need to tell it what data set you're using. So cough, cough, change this to homework 2 if you need to in your homework, cough, cough. On the model statement, y equals the x predictor, so in the same order as you would write in an equation. And then this magical option right here, STB, stands for standardized. And here's the output that we get. There is a new column out to the right relative to what we got in Proc GLM that has the standardized estimate. That's my standardized slope. That's my Pearson correlation between education and income. And here's my standardized intercept, which is always, always, always 0. Because in standardized space, every variable has a mean of 0, so there's nothing for the intercept to adjust for. The intercept adjusts for mean differences otherwise. In theta, you don't have to learn anything new other than one little 4-letter word. Maybe not the 4-letter words you're used to using when you run stata, a new one. Beta, because for better or worse, standardized slopes are often referred to as betas. So comma and then a beta adds the standardized slope to the end of your stata output. And in R, it's still LM, but there is a twist to referring to the variables in the formula. So before it used to be formula equals income squiggle 1 plus education. Now wrapped around each of those variables is a function called scale. That standardizes the 2 variables into a z-score metric, so then their slope is a standardized slope. And the output gives you the slope in Pearson correlation standardized units. So not bad. So rerunning the model with a couple extra options gets you the standardized slope, which is your measure of effect size. Okay, how are we doing? What does tilde stand for? Tilde would normally be equals, like if this were an equation, but equals was already taken. So tilde just means like y and then is going to be predicted by. Otherwise, if this was an equals here, R would get confused. Because formula is all this stuff at once. And if there's an equals, it would think that it's stepped into a different argument to the function. Okay. Questions? Yes?
Do you have specific numbers or range to decide whether these 2 factors are strongly correlated or weak correlations?
So the question was, do I have specific numbers I'm looking for to characterize whether these things are strongly related? Conventionally, yes. There are sort of standards for what is a strong, medium, or weak relationship. However, those tend to be not very useful across all disciplines there is an article on your reading list. I'm not sure which week I put it in, but it's talking about relying on Cohen's definitions of small, medium, and large. I want to say that in that old school way of talking about it, an R of 0.1 was small, 0.3 was medium, and 0.5 was big. But that pays no attention to the context of the data and what a good effect would be. So what I would say is 0 means nothing and 1 is perfect. And beyond that, it's a continuum.
It depends on discipline.
It does. I think it depends on discipline and purpose. Are you trying to save lives, or are you just trying to show relationships? A small effect size that saves lives, I think, is still important. But the smaller this number is, the harder it is to find that it's significant. Okay. Other questions? All right, Zoomers, still good? Okay. All right. Then let's go to the next model, because you already know how to do this. This is a new predictor, so we're swapping out a quantitative measure of education for a binary measure. Now, what's a binary variable? What do I mean when I say something's a binary variable?
They have two variables?
Two possibilities. Yep, so it's dichotomous. So we're going to use a dichotomous or binary predictor in the same model, and it's going to be marital status in this example. Got a question. By standardized, does it mean that it comes on a normal distribution, the t-score? By standardized, it means that it has, the solution has transformed all of the variables to a common standardized scale that's z, actually. And not to be confused with z standard normal distribution, which is a separate thing, even though they're both called z. A z-score variable has a mean of 0 and a variance of 1. So that's what I mean by standardized, is it puts everything onto the same metric so that you don't have to keep track of what the units are to make the slope make sense. So binary predictor. So I have a variable in the data set as to whether or not someone is married. I'm looking at whether people who are married individually, this is individual income, make a different amount of money on average. So I can guarantee that if you've taken intro stat before, you've seen this and it was called something else. I can guarantee it. So let me put this to you a different way. What if I wanted to ask whether there were mean differences between two independent groups? Does that sound like a thing you would have done? That used to be called a t-test. That's what this is. A general linear model predicting a quantitative outcome from a two-group predictor is the same thing as what we would call a two-sample or independent groups t-test. I personally think the name t-test for that is not helpful, because everything we're doing is a t-test. We have a t-test statistic for every kind of slope. So t is much more general than just that one instance, but that is what it is called. So this variable that we're going to put in the model is coded 0 or 1. And even though it's a categorical variable, it is still okay for us to put it in as a 0-1 predictor, because there's only one difference that is possible. I have a 0 or a 1. So when I think about what a slope means, the slope is the change in the outcome for a 1 unit change in a predictor. A 1 unit change in this binary predictor means going from a member of the 0 group to the member of a 1 group. A 1 unit change is the shift between two groups. And that's why we can do it this way, because there's only two groups. Next week, we'll see what happens for 3 groups and 4 groups. Okay, ready to see it? So this is actually easier, because the results that we're going to get are right here, and I'll show you how the code got us there. There's only 2 possibilities. the fixed intercept is going to become 14.45. That's going to be the best answer for our data. And the definition of a fixed intercept from before still, fixed intercept is the expected outcome when what is true? When x is 0. Exactly. So here, I got to know who's the 0 group. And the fixed intercept is the predicted mean outcome for that group. The way that I've coded this is that 0 is somebody who is not married and 1 is somebody who's married. So my fixed intercept here is going to be the predicted income for somebody who is married equals 0, meaning not married. The slope then, beta 1, a slope is the change in y for a 1 unit change in x. So the slope is the change in income from moving from the 0 group to the 1 group. The slope is the mean difference between groups. Question, if it's a binary variable, why does the xi get multiplied still in the same way as a quantitative variable? So married gets a higher number. Because the program doesn't care that it's binary. The math is the same, whether it has 0, 1, 2, 3, 4, or just 0, 1. In this case, there's only 2 possibilities for what this predictor could be. Either you're in the 0 group or you're in the 1 group. And so the only data that's available to make the slope is the mean difference between these groups. That's what it has to become. So you are correct in that the people who are married have a predicted outcome of 20.67 because they get the intercept plus they get the bump for being in the 1 group, whereas the people who are in the 0 group, this part drops out, and their predicted outcome is just from the intercept alone. Did that answer the question?
But if it was the opposite, like if we choose to put 1 for unmarried and 0 for married, then I think then the score would be the opposite, right?
If we switch the coding, is the question? That is a great question because in order to interpret this slope, I gotta know who's who. So what if I decided that married people should be the 0 group and unmarried people should be the 1 group? Can I do that? Sure I can. It doesn't matter. Somebody's got to be 0 and somebody's got to be 1, but it's up to you who's who. Now, given these are the means, like I could run proc means for the married people and the unmarried people, these would be the numbers I get either way. If I switched the coding, if I switched who is the 1 and who is the 0, I would get this exact same slope back as a negative number. Because this slope is telling me how the 1 group differs from the 0. The 0 is my you are here sign reference. The 1 is the coefficient applies to the 1. So in this coding scheme, the 6.22 means the 1 group is higher. If I switched who was 1 and who was 0, then the 1 group would be 6.22 lower and the slope would be negative. So yes, the same thing is true in correlations with binary variables too. In order to know what to do with a positive correlation, you got to know who's the 0 and who's the 1. Because that tells you which way is up. The slope tells you how the 1 group differs from the 0 group in that way. And I'm going to say it over and over again because it's easy to get confused. It's not just the group difference. It's how 0, saying it backwards. It is how 1 differs from 0. The intercept is given to the 0 group. The slope then kicks in to move to the 1 group, a 1 unit change. And question then following up, if I switched the coding such that the 1 group were the 0, then yes, the fixed intercept would now be 20.67 instead, because that's when the new coding scheme would be 0 for all the predictors. So the first step that we got to do is to make this new variable. So in the same way that we had to center education at 12 years to make 0 mean something, this variable is originally coded in my data set as 1 and 2. Now if I left it like that, the slope would be fine, but the intercept would be messed up, because the intercept would still refer to a 0 group, even if the numbers that are possible are 1 and 2. So it's the same weirdness that you get when 0 is outside the scale of the X predictor. We're going to fix it. So I have it new variable, and then the model with the new variable in each of the programs here. In SAS, keep in mind that any transformations to data have to happen within this data set combination, so it knows which data set it's going into to do things to. I'm creating a brand new blank column. So I'm calling my variable Mary01, because that's the 2 values that I'm going to have, and setting it equal to a dot, which in SAS means missing data. I'm then saying if the old variable, which is called Mary, was a 1, then make the new variable a 0. And if the old variable was a 2, then make the new one a 1. So this is a longer way of saying -1. But this way is more general for different types of situations. So then Mary01 goes in my model right here. I can ask for predicted means for each of my groups by filling in the equation. So in these predictive statements, the words refer to what the beta is going to be. So I'm saying, okay, take beta 0, give me one of those, and add to it the slope. So Mary01 refers to what the beta 1 slope is going to be, but times it by 0 because I'm talking about the 0 group. And the second line adds beta 0 plus beta 1 times 1. So this out here is me being nice, by the way. This is not SAS code that, well, I'm trying to tell you what the lines are doing. So now I have all 3 pieces of information. I know what the mean's going to be for the 0 group. I know what the mean's going to be for the 1 group. And the model slope is going to tell me the mean difference. So here's my results. The things that I need to watch for: mean square error. That's going to be the first question for each model on your homework, because if you get mean square error right, otherwise known as residual variance, you have the right model. Second question, what's your fixed intercept? If you get the fixed intercept right, not only do you have the right model, but you have the right predictor coding for what 0 means. So these are the numbers that we saw up above. That's my 14. The intercept is the expected outcome when the predictors are 0. That means that's the expected income from my 0 group. A slope is always the expected change in the outcome for a 1 unit change in X. That corresponds to going from the 0 group to the 1 group. The fact that the slope is positive means the 1 group is higher on average. As before, slope estimate divided by its standard error for expected inconsistency across repeated samples gives me my friend T. And if you had done this in intro stat class as an independent samples t-test, there's your T. It would work out to be exactly the same thing. But doing it in a linear model allows you to add in other variables at the same time, as well as extend the model to more than 2 groups. And then here's my predicted means for each of the groups down here, as well as confidence intervals for them. So, any questions on the SAS code? Yeah, or otherwise?
So versus estimate,
Mm-hmm.
in both of those, is it running 2 different linear models and then comparing them?
Nope, it's one model,
Okay.
but I'm asking it to do math on the results of the model. So I am creating a linear combination of the fixed effect estimates, each multiplied by the value of the variable that I want to create the predicted outcome for. So what this is doing under the hood is taking whatever beta 0 is going to be, multiplying it by 1, then adding to that whatever beta 1 slope is going to be and multiplying it by 0. And the reason it's being multiplied by 0 in this line is because I want the predicted outcome for the unmarried group, and that's who is coded 0. So I don't technically have to write this. It's kind of here to make a point of comparison against the second line. Technically, this is the only line I have to write, because that is given as beta 0 plus beta 1. And you could do that on your own, right? Like, you could just get out your calculator and add those two numbers. But what you can't get from your calculator as easily is the standard error that goes with that. So not only do I get the 20 down here, I get the standard error for the 20. And that would allow me to put error bars on a figure to describe the expected inconsistency of those estimates. Okay. Other questions? So in the other programs, Stata code looks similar, but it is logically backwards in how you create the new variables. So in Stata, I'm creating the same new empty column. Gen is the command, it stands for generate. And it's empty because I'm setting it equal to a 0. And then the replace option says, replace the new variable equals 0 if the old variable equals 1. So replace new if old, rather than SAS saying if old then new. Now I want to point out something that is not a typo. Equal, equal. Have we seen this before in this class? I don't remember. No, that was the other class. Okay. Equal, equal is used in Stata and in several other programs to indicate a logical evaluation. So if it's equal to is what that means. So the first equal by itself is setting an equal to 0. The second equal equal is like, if this is true, then do that. So new variable is first, old variable is second in Stata. And then the regress command is now using the new variable, and the analog to estimate statements in SAS that allow you to get linear combinations is lincom. It stands for linear combination. And here, Stata code makes what's happening a lot more explicit. So underscore CONS stands for the fixed intercept. Take the fixed intercept, multiply it by 1, and then add what the fixed slope is going to be and multiply it by 0. And that creates the predicted mean for the 0 group. If I do the same thing but multiply the slope by 1, that creates the predicted mean for the married group instead. So this is really the only one that's new information. I just wrote them both out for completeness. And otherwise, the results look exactly like SAS, just with separate tables for the new pieces of information. There's my mean square error residual variance. Okay. Questions on Stata code or output? All right, then R. More code, of course, in R than the other programs, but that's how it works. So first step, make a new variable. So example 2 is the data set that it's going into. The new variable is called Mary01. I'm setting it equal to NA, which means blank, missing data, not applicable. And then recoding the new variable into either 0 or 1. And then the interior of this is like the if part. If the old variable was 1, then make it a 0. If the old variable was 2, make it a 1. And note the double equal here for the same reason. It's a logical equality that it's evaluating. Then in the model, formula equals income is my outcome variable, squiggle 1 for the intercept plus Mary. I'm saving the output from this analysis as an R object called model Mary 1, because then I can ask it to get residual variance for it, the output itself, as well as confidence intervals for the output. And then the last piece to get the linear combinations, this ugly thing right here, GLHT is the name of the function I'm using. That stands for General Linear Hypothesis Test. I'm using the output from the model in it. And then each of these statements is requesting a different predicted income, where the numbers, right here, the order of the numbers corresponds to the order of the fixed effects up there. The numbers in each spot in this little C thingy are multipliers. So in R, both of these little lines start with a 1, because to create a predicted income, at a minimum, I need the fixed intercept. So I need 1 times beta 0 to start with. That's why I put the 1 up here in my formula, is to remind myself that that's the first thing. Because otherwise I'll forget, and then the order will be off. So then the second number is the multiplier given to the slope. So if I'm creating a predicted outcome for the 0 group, I want the multiplier to be 0 times the slope. And if I'm creating a predicted outcome for the 1 group, then I want the multiplier to be a 1 for the slope. And then the rest of this is just spitting out that result without adjusting the p-values and adding confidence intervals. So those of you who are working in R, find and replace is your friend, okay? You will note that I name things in particular ways, like I have model Mary 01 is the name of my model, results, and then it's Mary 01 because that's the variable. And so you'll see that here, 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 and then it switches to prediction because that's the result of this process, which is used here and here. So if I'm trying to rewrite this code to work for a different problem, find and replace Mary 01 with whatever your variable is called, and it changes it everywhere. The same is true in the other packages, but you don't have to do quite as much typing in those. But find and replace will be your friend. Question or yawn?
Question.
Okay.
In the, I guess it's like the third paragraph down where it says print,
Yeah, paragraph is accurate. This thing?
Yeah.
Okay.
Those first 2 lines,
Mm-hmm.
will we be putting those in our code, the print piece?
So the print is, these are basically my notes to you about what is happening next.
Mm-hmm.
And I put them in prints so that when I output the results of my program, it actually shows in the window, because the program that I'm using doesn't print comments to the window.
Mm.
So you do not have to have these.
Okay.
But what I do when I finally figure out how to do something in R is immediately write down what it does.
Mm-hmm.
Because then 6 months from now, when I look back at it, I won't know anymore what I did.
Mm-hmm.
So you don't have to have these, but what I'm trying to do is describe as much as I can using words of what's happening subsequently. And yeah, I would think of these as paragraphs, because like this chunk is making the variable.
Mm-hmm.
This chunk is estimating the model and getting the model output that I want. And then this final paragraph is using the results of the model to get predicted outcomes that I want.
Right, okay.
So yeah, my spacing in paragraphing is deliberate. R doesn't care, but it makes your code easier to read if you can like have a rhyme and reason to how you to do things. So then we end up with the same stuff. My mean square error first, my intercept and my slope, and then the estimate statements out of GLHT down there for the 2 predicted means. All right. 303. Other questions so far? So just as we wanted to have an effect size for my slope for a quantitative predictor, I want to have an effect size for my slope for a binary predictor too. Same problem. I know that the difference in thousands of dollars of income is 6.22. I don't have a sense of, is that a lot? Is that big? I know that it's significant, but that could be because I have 734 people, not because it's that big of a difference. So I could ask for a standardized slope and get a Pearson's correlation for this too, and that would be fine. There'd be nothing wrong with that. However, when you're talking about group differences as the thing you're trying to quantify an effect for, there's a more natural effect size known as Cohen's D. Hedges, G, deltas, something or another, there's a whole bunch of them, but the general heading for this is standardized mean difference. How far apart are the group means in a standardized metric? So this process I'm about to show you is equivalent to computing Cohen's D using the two means and the pooled standard deviation, but instead I'm going to do it using the model output, because using the model output generalizes to much more complicated things. So this will be the one thing in your homework that I want you to compute by hand, and in the next unit I'll show you how to make R, SAS, and Stata do it for you. Right here. You can compute a D standardized mean difference using the t-test statistic for your slope. So let me see if I can get them all on the same page here. I don't think I can. So here's my slope out of the model. The 6.22 is the mean difference for how the one group differs from the zero group. And the t-test statistic that goes with it right here, that t-test statistic goes into the D in the numerator times 2. And the denominator is the square root of the denominator degrees of freedom, which is sample size minus the number of fixed effects. So in this example, I have 734 people. I got 2 fixed effects. I got a fixed intercept and a fixed slope, so that gives me 732.
How do you know the fixed effects, number of fixed effects again?
Because if I go up to there's a couple ways. Number of things after the squiggle.
Okay, that's fine.
Or equivalently, number of rows in your results table under estimate here.
Okay.
Yep. At a minimum, you got a fixed intercept, and then you get a fixed slope for each additional predictor that you add. So that works out to be a D of 0.462, which means that these two groups differ from each other in predicted income by 0.4 standard deviations. Unlike R, D is not bounded. You can have negative D's or positive D's, and they can go on from positive to negative infinity. So D is harder from the perspective of, like, is that a lot? But it's in standard deviation units. So basically these two groups are like a half a standard deviation apart. That's what this means. Question?
So that means that if there's a 68% of items that are equal between one of those things?
There's what? I'm sorry?
Between those two things, there's a 68% of comparability. That's what I'm
68% comparability. Where are you coming up with that?
Out of, well, I guess the standard bell curve, and ask you.
Oh,
the one in the middle, which is in a 68.
yeah, 68% is within plus or minus 1 standard deviation on either side. That's actually 2 because it's plus or minus 1.
Oh, okay.
So I don't know that works, but I know that people have come up with sort of rubrics in that same idea of like percent overlap. I'd have to do some digging. I know I could probably find some articles that phrase it that way, but I know that if you're planning like an intervention study, a D is a common unit of effect size for like how effective your treatment is, like how much different is your treatment group than your control group.
Oh,
There is a formula, by the way, where you can get from D to R and back again. Do I have it in here? Yeah, I do. Slide 52, by the way, that's where these formulas are. D you can get from your t-test statistic, R you can get from your t-test statistic, and you can get D and R from each other. So where this shows up as useful is if you're doing meta-analysis and you're trying to get an effect size out of studies that might not necessarily report it in the way you want. If they do report other things, you might be able to back-translate your way into what you want with all of these conversions. So we'll see more of this later on. In the code, let me go back to this thing. So in SAS, I made it do math by starting a new data set and saving this as a variable and then printing the variable. In Stata, you can do math by using it as a calculator. Just type the word display, meaning print this, and then I typed what I wanted it to do, and that's the number I got. And I did the same thing in R. I saved it as an object called Cohen's D and then asked it to print it. So you can actually use your software as your calculator. What I want to show you next time, which I just figured out in all three programs, is how to make the program take the saved T result and do it for you so that you don't have to manually type in the numbers, because then it goes much more quickly and there's less error involved. So that's coming next unit. Okay. Other questions on that? And as I promised, words. So with respect to the quantitative predictor, I've got a paragraph about that. So in your homework, you will complete paragraphs that look like this. Because writing results sections is literally so formulaic that I could write a SAS program to do it. I'm dead serious. Things are written in a certain way and it's all conditional. Like if the slope is positive, say higher. If the slope is negative, say lower. If P is less than 0.05, say significantly. If P is greater than 0.05, say non-significantly. So I would recommend reading through this as sort of an orientation as to what the drop-down menus are going to be looking for. And then with respect to the binary predictor, I have two alternative paragraphs. One that describes it from a linear model's point of view, where I'm emphasizing what the intercept is for the zero group, and then how the slope tells me how the one group differs from the zero group. And then the second paragraph about it describes it as a two-sample t-test instead. The t is the same either way. It's just what are you emphasizing in your story? Do you give the means and then talk about the difference, or do you give the intercept for one group, which is the mean for the zero group, and the slope to get to the difference? So 6 of one, half dozen of the other. And in case you have not seen how to do things like Pearson correlation in software before, I have a bonus. Bonus meaning you don't need this for your homework, but I wanted to show it to you in case you hadn't seen it. Proc core is how you get correlations in SAS. You can do Pearson's or Spearman's, Kendall something I think too. There's a couple. So this is a correlation matrix among the three variables that we looked at. I also asked it to do confidence limits for the correlation. So do you remember like Fisher's R to Z? Did anyone have to do that? Do we still do that in IntroStat? No? Not a thing? Okay. Well, it was a hand calculation I learned like 30 years ago that it will do for you. So that's where I was going with this. It's yet another thing that software does faster and better than people. In Stata, it is the command pwcore for pairwise correlations, and it computes a little correlation matrix like this, where what you get are correlations and p-values. The confidence intervals for the correlations is a special thing I had to download, so I have the code that I use for that. And then in R, it's the core option followed by core test to get confidence intervals. So if you don't know how to do that already, then this is how to do that piece of it in software as well.
Can I ask understanding question about
Please.
those confidence levels? So I'm looking at the bottom one for the R.
Yes.
It says, the top one says 0.38, then 0.22, and then 0.05.
Mm-hmm.
So if I'm reading that, then the strongest correlation is between income and education level.
That is correct.
Okay.
Yeah, so this is the correlation between income and education, which is 0.38, but the confidence interval around it is 0.32 to 0.44. So like once you factor in the expected inconsistency, that's the range that you would see it in.
Mm-hmm.
Whereas the correlation between marital status and income is only 0.22.
Mm-hmm.
So that R is what we just found a D for instead, but you could go back and forth. And then the last one, there is no correlation between education and marital status. The correlation is only 0.05. The confidence interval overlaps 0. And the fact that the confidence interval overlaps 0 means it's not significant.
Okay.
Not significantly different than 0 as the null hypothesis. So,
Gotcha.
yep. All right. Other questions? Okay, then we got very close to getting all the way through this with a few slides left with respect to power and sample size planning, which will start next week. Then follow with some new stuff. So 3:14, anything else before we adjourn? All right, then thank you for being here as always. Have a great weekend. We'll see you next week. Let me know if you need anything. Bye, folks.
Thank you. See ya.
Thank you.